So, hi everybody. Today's lab is all about torque. So before we get into the experiments that we're going to do today, let's talk about torque, what it means, and how you can calculate it. So torque is what we call the rotational analog of force. It has a lot of similarities to force, but it's used in the context of rotation. So we can think of force as the cause of linear motion. In other words, if something is at rest, you need to apply a force to it to get it to start moving, to get it to accelerate and begin to move. By the same token, if you have an object that has some kind of rotation axis or pivot point that it can rotate around, you need to apply a torque to it to get it to start moving, to get it to start rotating. Okay? So that's the way in which torque and force are kind of similar concepts. They're both the cause of motion in some sense. So how do we calculate torque then? Well, let's imagine we have a rigid object right here. It can have any shape you want, but I just drew this oddly shaped object just for illustrative purposes. And this is our pivot point down here. So the object is attached to this pivot point. It's free to rotate around that pivot point. Over here, shown with the X, is where we apply a force. We can apply a force at that point. It can be in any direction you want. So there are two vectors right away that we need to sort of point out here. The first one is a vector which we'll call R, or the radial vector. That points from the pivot to this point where the force is applied. That's the radial vector R. F is just our force vector, and again, that can be in whatever direction. So right away we notice that these two vectors, R and F, they make some angle with respect to one another. So we'll call that angle theta. Okay, so finally, the equation for torque is given up here. It's just the cross product of those two vectors, R and F. So torque, given by the Greek letter tau, is a vector which is the cross product of R and F. So any cross product between two vectors gives you a vector. So torque is a vector itself. And like any other vector, we can refer to it in terms of its magnitude and its direction. Okay, so how do we think about the magnitude? Well, this is how any cross product works. You take the magnitude of the first vector, the magnitude of the second vector, times the sine of the angle between the two vectors. That's how you calculate the magnitude of any cross product. So in the case of torque, the magnitude is going to be magnitude of R, which is just the distance between your pivot point and the point where the force is applied, times the magnitude of F, just how strong the force is, and then sine of the angle between those two. If we want to know what the direction is, then we can use the right-hand rule. So if you remember how the right-hand rule goes, with a cross product of two vectors, you start by taking your right hand, and by the way, don't use your left hand because you'll get the wrong answer every time. Take your right hand and point it in the direction of the first vector, which is R. Okay? And then you curl the fingers of your right hand in the direction of that second vector, which is F, like this. Now your thumb is going to be pointing in the direction of the cross product. So in this case, what we'd say is the torque is going out of the page, like this. So your thumb is pointing in the direction of the torque, which in this case is out of the board, like that. Now what is that actually telling you? Well, here, think about this. If I take my thumb and I point it out of the board like this, my fingers are going to be curling in the direction of the rotation that's going to be induced by this torque, right? We expect that counterclockwise rotation is going to be induced with a torque like this. So that's how we calculate torque. So here's the setup for the first experiment. We have a meter stick, and it's attached to a pivot point at this end, and the meter stick is free to rotate around that pivot point in either direction, but it's not rotating. The reason it's prevented from rotating is because there are two torques that are acting on it, and they exactly cancel each other out to give you zero net torque. So one of the torques comes from gravity. So gravity acts at the center of mass of the meter stick, straight down, and if we do the right-hand rule, we can see that R cross F gives us a torque which is counterclockwise, like this. On the other hand, there is a string connected to the meter stick right here, and there's some upward tension in that. So if we do the right-hand rule, R cross F, we'll see that this gives us a torque which is clockwise. So we have the counterclockwise torque due to gravity, the clockwise torque due to the tension in the string here, exactly balancing each other out so that the meter stick doesn't rotate. So in this experiment, what we're going to do is we're going to move the string to various points along the meter stick. So we'll start with it over here at 90 centimeters, and then we'll move it in closer and closer to the pivot as we go. And each time we do that, we're going to measure the force of tension in the string in particular, and we're going to do that using the force probe. Okay? So what we're going to be looking at is how does the force of tension that holds the meter stick in place change as we move the string to various positions along the meter stick. That's what we'll be looking at in this experiment. Okay, so for the first run of the experiment, we're going to have the string at the 90 centimeter mark of the meter stick. Okay, so it's right over here. Again, the string is perfectly vertical and connected to the force probe, which measures the tension in the string. So what we want to do is get a really accurate reading of what the tension is right now. And so the way we'll do that is by first lifting up the meter stick so the string goes slack. There should be no tension right now. And I'm going to zero out the force probe. Okay? So when the string is completely slack, I've zeroed out the force probe. And now I'm going to set the meter stick back down. And now we can measure the tension, which is 0.842 newtons. So 0.842 newtons is the tension force when we have the string at the 90 centimeter mark of the meter stick. Okay, so for this next trial of the experiment, we now have the string at the 80 centimeter mark of the meter stick. So we've moved it in a little bit towards the pivot point, and we're going to do the same procedure to measure the force of tension in that string. So we'll start by holding the meter stick up so that the string goes slack, zero out the force probe. So now the force probe is reading 0 newtons as we want it to. And then I'll set the string down like this. So now it's got some tension in it. And now the tension we're reading is 0.945 newtons. So 0.945 newtons is the force of tension. Then we have the string at the 80 centimeter mark in this experiment. So the rest of this experiment goes in pretty much the same way. Each trial, we're going to move the string 10 centimeters this way, closer to the pivot point, and then we'll measure the force. And we'll keep doing that until we get to a distance of 20 centimeters, and that will be our last trial for this experiment. I'm not going to show you all those trials. Instead, I'll just flash the data for the remaining trials on the screen here. So here it is. So there are a few more measurements we need to make before we're done with this part of the experiment. And the first thing is, where is the pivot point on the meter stick? So it's pretty close to the very end of the meter stick, but it's not exactly there, right? There's a hole in the meter stick that is acting as our pivot point, and that is exactly at the 1 centimeter mark. So the position of the hole in the meter stick is at the 1.0 centimeter mark on the meter stick. Okay, so here is the final set of measurements that we need to take in this experiment, and actually these measurements are going to be important in the next experiment as well. What we want to know is, A, what is the weight of the meter stick that we're using here? And B, where is the center of mass of the meter stick? Because the center of mass is the point where gravity effectively acts on the meter stick. So we're going to need to know that. Now, the way we can find the center of mass is actually by removing the meter stick from the pivot here, and then hanging the string vertically like this, and then just seeing where we have to put the string so that the meter stick balances, okay? If the string is not right on the center of mass, the meter stick will tip one way or the other. But if it's right on the center of mass, then we can actually get it to balance. So you kind of expect that the center of mass of a meter stick would be right in the middle. And that's certainly true if the meter stick is perfectly uniform. But if the meter stick has any kind of non-uniformity to it, the center of mass might not be exactly right in the center. But in this case, I'm getting the meter stick to balance right now, and the string is right at the 50 centimeter mark. So the center of mass is at the 50 centimeter mark of the meter stick. And then furthermore, I can measure the weight of the meter stick just using the force probe, because again, it's this tension that's holding the meter stick up right now. Whatever the tension is, that's the weight of the meter stick. And that is 1.517 newtons. So that's the weight of the meter stick, 1.517 newtons. So this is our setup for the second experiment. The basic idea is very similar to what we did previously. We still have the meter stick connected to a pivot point, and there are two torques acting on the meter stick. One of them is due to gravity, the other is due to the tension in the string here. And they exactly cancel each other out so that we have zero net torque and the meter stick is not rotating. But in this case, instead of having the string make a right angle with the meter stick throughout the experiment, instead we're going to change the angle and then see how that affects the force that we read out each trial. Okay, so we're basically going to start here and then gradually decrease that angle and see how that affects the force in each trial. Alright, so there's one thing about the setup that's different from before, which I forgot to mention earlier. That is the metal clamp that connects our string to the meter stick. This metal clamp is going to be kept at the 90 centimeter mark of the meter stick throughout the experiment. So the metal clamp is at 90 centimeters on the meter stick. So the way we set up the first trial is by putting the force probe on the stand here exactly 1 meter above the pivot point down here. Okay, so in other words, if you look at where the force probe is attached and you look at the pivot point down here, this distance is exactly 1 meter. Now, after we set up the station this way, we need to measure a couple other distances. So the first one is, what is the distance from the meter stick to the hook of the force probe right here? Okay, so let's measure that. It's going to be a little less than 1 meter this time. And what I'm getting is about, that's about 93.5 centimeters. So in other words, the distance from the meter stick to the hook of the force probe is 93.5 centimeters, and we call this HH. That's just the variable we're going to give for that height. Okay, the next thing, what is the total length of the string from where it's attached to the meter stick down here to the hook of the force probe up here? We're going to call that length L, and we're going to measure it directly using this 2 meter stick. And so what we're getting here is about 123.2. 123.2 centimeters is L for this first trial. Okay, then the last thing we're going to measure, what is the force? What is the force of tension in the string that's holding up the meter stick? So like we did before, I'm going to hold up the meter stick, make sure the string is completely slack, and then zero the force probe, then set it back down, and then the force that's being read out is 1.398 newtons. So the force of tension for this first trial is 1.398 newtons. For this next trial, I set the force probe a little bit lower, and so what that does is decreases the angle of the string relative to the meter stick here. So now the distance from the pivot point down here to where the force probe is attached up here is 90 centimeters. Okay? So we'll go through the same set of measurements as before. The first is, where is the hook of the force probe? How high above the meter stick is that? And so we can measure that directly. And what I'm getting is exactly 84.0 centimeters. So 84.0 centimeters for that distance. Okay, next. So that's HH, 84.0. Next, let's measure L, the length of the string. And again, we'll use the 2 meter stick for this. So what I'm getting is 115.5 centimeters. So 115.5 centimeters is L for this trial. And then finally, we'll go ahead and measure the force. First, zero out the force probe with the string slack. And set it down so we can measure the force. And what we're getting is 1.472 newtons. So 1.472 newtons is the force for this trial. So now you have a pretty good sense of how that second experiment goes. Basically, each time we do a trial, we lower the force probe on that vertical stand, and in doing so, we decrease the angle that the string makes with respect to the meter stick. So we'll continue doing that using smaller and smaller angles for 4 more trials. And rather than showing you all of those trials on the video, I'll just flash the data up on the screen after the end of this video. And that's it for today. So, as usual, follow along with the worksheet that I provided that accompanies this video, and that will show you how to do the analysis. And with that said, we're done for today, but I'll see you in the next lab video. So take care out there.